We begin with a Bose-Einstein condensate of dysprosium-162 atoms. To a good approximation, this condensate is very close to absolute zero temperature and sits at equilibrium inside of the optical trap, as you can see here in this animation. We are now going to expose this condensate to a precisely timed two-pulse sequence of light. We'll just pause the animation here to briefly explain the purpose of this. The additional laser beams create a lattice along a certain axis, shown schematically here. Due to the wave-like properties of the Bose-Einstein condensate, the atoms diffract from this lattice. The precise timing of the pulse sequence is engineered such that the condensate is basically split in two, with half the atoms moving in one direction and the other half along the opposite direction. We'll now resume the animation. Immediately after the pulse sequence, the trap is then switched off, and the two oppositely propagating clouds are left to collide and expand. We measure the cloud by taking an absorption image. In addition to the two large and oppositely propagating clouds, one clearly observes particles have appeared on a spherical halo. These are atoms which have collided with other atoms. Now here is where things become interesting to us. We have chosen dysprosium for a specific reason. Dysprosium has a permanent magnetic dipole moment of almost 10 Bohr magneton. For an atom, this is absolutely huge. In fact, it is among the largest of all known stable elements. So these dipole-dipole interactions are very strong. They are also long-range and anisotropic. It turns out that the way the atoms have distributed themselves on the spherical halo is exactly determined by these dipole-dipole interactions. Furthermore, by changing the axis along which the dipoles are aligned relative to the collision axis, we can profoundly change this distribution around the sphere. So in this case, we note that the dipoles were aligned parallel with the collision axis. If now we were to repeat the experiment, with the dipoles now aligned perpendicular to the collision axis, a dramatically different distribution appears around this sphere. Our work contributes towards a growing understanding of the fundamental elements in strongly interacting quantum matter, particularly that where the microscopic elements have strong electric or magnetic dipole moments.